In this lesson, we're going to cover cryptographic attacks. Now, cryptographic attacks refer to techniques and strategies that adversaries employ to exploit vulnerabilities in cryptographic systems with the intent to compromise the confidentiality, integrity, and authenticity of your data. These attacks are there to defeat the cryptographic protections, either by deciphering encrypted data without the appropriate key, impersonating another user, or creating forgeries that cryptographic systems would deem authentic. These methods can range from exploiting weaknesses in cryptographic algorithms and protocols to leveraging flaws in software implementations or simply using brute force techniques to guess the key. For our purposes in this lesson, though, we're going to focus on attacks related to downgrade attacks, collision attacks, and the threat of quantum computing that is looming over all of our existing encryption algorithms. Now, first, we have downgrade attacks. At its core, a cryptographic downgrade attack, also known as a version rollback attack, will aim to force a system to use a weaker or older cryptographic standard or protocol than what it's currently using. The idea here is that by rolling back to these outdated versions, an attacker can exploit known vulnerabilities or weaknesses in those older protocols that have now been addressed in newer or more secure versions. For example, let's pretend that we have two people, Alice and Bob, and they want to establish a secure connection channel between their systems. Now, most modern cryptographic systems will support multiple versions of a protocol to ensure for backwards compatibility with older legacy systems. When Alice and Bob begin their handshake to establish that secure connection, their systems will typically communicate the version of the protocols that each one of them can support. And then their systems will agree to use the most secure version that both of these systems can understand. For example, if I speak English and Spanish and you speak Spanish and Chinese, we would agree to speak Spanish because both of us understand that language. So, going back to our example, let's pretend that we have an attacker named Eve, and she wants to be able to intercept this communication between Alice and Bob. To execute this attack, Eve will try to manipulate the messages being sent between Alice and Bob's computer to establish this handshake and decide on a version to use. This way, they can manipulate the message to say the highest version that both parties support is in fact an older, less secure version. Now, Alice and Bob's systems, unaware of Eve's interference, will proceed with the outdated protocol, and this makes all their communications susceptible to vulnerabilities inherent in that older version of the encryption algorithm that Eve can now take advantage of to be able to see everything they're sending back and forth. One infamous real-world example of this type of downgrade attack involves the use of the Poodle attack, known as the Padding Oracle on Downgraded Legacy Encryption attack, which targeted SSL version 3.0. Now, despite the availability and widespread use of a more secure protocol like TLS, many systems still supported SSL 3.0 for backward compatibility. Poodle tried to exploit this by forcing its victims to revert to this older, more insecure protocol, and this would allow attackers to extract sensitive data from these communications. So, why are downgrade attacks so dangerous? Well, these downgrade attacks are dangerous because they turn the very nature of evolving security, such as the development of a stronger, more robust cryptographic protocol, against itself. In trying to be more inclusive and comprehensive, our systems that maintain this backwards compatibility with older standards are unknowingly leaving themselves open to these types of downgrade attacks. But it's not all doom and gloom. Awareness of downgrade attacks has led to the development of countermeasures to help prevent them. For instance, many systems have phased out support for legacy protocols that are known to be truly insecure, even if it means sacrificing backward compatibility. In other scenarios, version intolerant checks can also be employed, where a system tests the waters by initially claiming to only support the most recent protocol version. If the other end user truly doesn't support the latest version, they will naturally respond accordingly, but if there's any interference forcing a downgrade, this will quickly become apparent. Second, we have collision attacks. Now, a collision attack aims to find two different inputs that produce the same hash output. This can be a vulnerability because hashing is commonly used for data verification. For example, when you're downloading a file from the internet, the website may provide a hash value for that file. Once you finish downloading the file, you can run it through a hash algorithm and calculate a new hash digest. Then you compare that to the one that's listed on the website. If they match, it's assumed that the file has not been tampered with. However, if an attacker can produce a malicious file with the same hash value by exploiting a collision, the user could be tricked into thinking they have a legitimate file when in fact they have a file that has the same hash value, which means it's subject to a collision. Historically, MD5, also known as Message Digest Algorithm 5, was a popular hashing function. However, over the years, many vulnerabilities in its structure made collision attacks much more feasible. Cybersecurity researchers were eventually able to create two different sequences that hashed out to the same MD5 hash, rendering MD5 unsuitable for further use in security certificates and encryption technologies. These collisions do undermine the trust and reliability placed on cryptographic tools, and they could potentially allow malicious actors to impersonate trusted entities, forge digital signatures, or distribute tampered data while appearing genuine. Now, the birthday paradox or birthday attack is a counterintuitive probability theory that plays a significant role in understanding collision attacks. The paradox itself posits that in a group of just 23 people, there's a better than even chance that 2 of them share the same birthday. Translating this to cryptography, the birthday attack refers to the probability that 2 distinct inputs or files, when processed through the same hashing function, will produce the same output, which we call a collision. Due to this principle, finding collisions in a hashing function might be more probable than initially perceived. For cryptographic systems, especially hashing algorithms with a fixed size output like MD5, SHA-1, SHA-256, and SHA-3, this means that vulnerabilities to collisions might arise faster than expected, and this underscores the necessity for robust cryptographic designs and frequent algorithm updates. Third, we need to talk about quantum computing and the threat it poses to our current cryptographic implementations and algorithms. Before we dive into the threat of quantum computing, we need to take a moment to define it. Now, quantum computing involves a computer that uses quantum mechanics to generate and manipulate quantum bits, known as qubits, in order to access enormous processing power. Now, I know this is a weird definition because in the definition itself, I'm using 2 terms inside of it, both quantum and computing. And in this case, I really don't like that definition, but there really is no better way to explain this. Now, when you think about a classic computer, like the one you're watching this course on right now, it's using ones and zeros to process information. The faster you can flip those bits and turn a 1 to a 0 or a 0 to a 1, that means the faster you can get information done and the faster computer you have overall. Well, at a certain point, we can't make our computers any faster by simply flipping bits. This means we've run out of computing capability. So, to overcome that, we started taking single processors and putting in dual processors, and then we made quad processors, which had 4 cores, and then we made octa-core processors that had 8 cores, and things like that as we kept speeding up our computers. Well, with quantum computing, it is a completely different ballgame. Instead of using ones and zeros, we use things known as quantum bits or qubits, and this can be done in computing or in communications. Now, when we deal with communications, we're talking about quantum communications being a communications network that relies on using qubits made of photons, or in our case light, to send multiple combinations of ones and zeros simultaneously, which will result in tamper-resistant and extremely fast communications. Again, I know this is really vague, but hang in with me here for just a second. When we talk about quantum, I keep talking about these things called qubits, and I talk about the fact that there's a difference between our traditional electrons, which are either on or off, ones or zeros, and this thing called a qubit. So let's talk about a qubit for a moment. What exactly is it? Well, a qubit is really just a quantum bit. It's composed of either electrons or photons, so it can either be electrical or made by light, and it can represent numerous combinations of ones and zeros at the same time, using something known as superpositioning. Now, this is really the main benefit of using a quantum computer over a traditional computer, because we're not just going to have a single 1 or 0. You can have multiple combinations of ones or zeros at the same time, and this would all be 1 qubit. So you can actually crunch through a wide variety of potential outcomes simultaneously. And so it's really great when you're trying to do a bunch of really complex math problems. And that's really the whole reason that we have quantum computing. When you think about quantum computing, it's never going to replace the computer on your desktop. That is not what it's designed for. Instead, it's designed for very specific use cases, such as very complex math problems, or trying to do something like modeling of an atom or some kind of atomic structure or something like that. Now, why should I care about quantum if it's never going to be something that's sitting on my desktop? Well, because there's one thing that quantum is really, really good at. And what is that? It's math problems. And if you think about cryptography, all cryptography is a bunch of really complex math problems. And so, because cryptography is used to secure our communications and our data by relying on how difficult a math problem is to compute with a traditional computer, this is actually something that gives us strength in cryptography. But if quantum computers are really good at doing math problems and they can do it much, much faster, that means our cryptography can actually be defeated and taken down by a quantum computer. And this is why we have to start thinking about this, because it's one of the things we rely so heavily on in cryptography is the key exchange using asymmetric communications. Now, one way we do that is with the public key infrastructure. Well, that whole concept is that we have to have a way to do a simple math problem to create a very complex thing that has a difficult time of being broken back apart. So, for example, if I take 2 prime numbers and I multiply them together and I give you the result, that result is really easy to calculate if you know what the two prime numbers are to be able to multiply them together. This would be, in our case, a public and private key that really represent two really large prime numbers. Now, once you have that result though, it might be a really large number, but there's only two things that can be factored into it. Those two keys, the public and private key that I just gave you. Those are our two prime numbers. Well, with quantum computing, they can make very quick work of this type of math problem, whereas our traditional computers can't because it involve taking that big number and dividing it by 1, and then dividing by 2, and then dividing by 3, and then dividing by 5, and then dividing by 7, and keep going until we get all the prime numbers and find the two factors. Well, with quantum computing, we don't have to do it that way. Instead, this becomes a relatively easy math problem, and we can crack it much, much quicker with a quantum computer. In fact, asymmetric encryption algorithms, which are those that rely on this hard math problem, have been mathematically proven to be broken by quantum computers. Now, the good news here is that at the time of me saying this, there are no real operational quantum computers in use. In fact, the only quantum computers at the time of me saying this are ones being used for prototyping and development on a very small scale, and governments and large companies are the ones who are spending enormous sums of money to create these small-scale quantum computers. Right now, the estimate is that we won't have a working quantum computer until at least 2030 for government and large corporate use. But consumers like you and I won't see quantum computers available until sometime in the late 2030s or early 2040s. But it is something we need to be aware of because our current encryption algorithms are not made to withstand the power of quantum computing. So, that brings us to this idea of how do you overcome quantum computers when you're dealing with cryptography, and that is post-quantum cryptography. Now, post-quantum cryptography is a new kind of cryptographic algorithm that can be implemented using today's classic computers, but would still be impervious to attacks from future quantum computers once they're in production and they are widely available. Now, there's really two methods that we use to try to create this post-quantum cryptography world. The first method is to just increase our key size and to increase the number of permutations that are needed to be brute forced. This works well when you're dealing with symmetric encryption algorithms like AES. If I take AES 128 and I increase it to AES 256, for example, I have doubled my key length from 128 bits to 256 bits. But I have actually squared the number of possible combinations that are going to have to be figured out by that quantum computer, and this extends the time and makes it much stronger and harder to crack. The other way we do this is by working on other approaches, and researchers are doing that right now. These are called post-quantum resistant algorithms. Now, these things are going to be looking at using things like lattice-based cryptography and super singular isogenic key exchanges. Now again, both of these terms are not something you need to understand or go in depth on. In fact, when we talk about quantum computing and quantum communications, we really need to think about qubits and all the stuff we're talking about with the word quantum, and I just want you to associate this with something that can be really easy to break apart our asymmetric encryption algorithms pretty quickly once it's in production, but it doesn't exist today yet. Remember, asymmetric encryption algorithms are the things that we use for key exchanges and digital signatures in a public key infrastructure, and that's really where the threat is when we start talking about quantum computers. Again, right now, we do not have any dedicated quantum-resistant cryptography yet, but in 2022, the National Institute of Science and Technology did complete a 6-year competition to select post-quantum cryptographic standards, and they ended up selecting 4 viable algorithms. For your general encryption needs, NIST recommends that you use the Crystal Cyber algorithm, which uses a relatively small encryption key and is focused on the difficulty of solving learning with error problems over modular lattices to provide a post-quantum encryption algorithm that is roughly equivalent to the strength of our current AES 256-based algorithms used in symmetric encryption. For digital signatures, NIST recommends you select one of 3 algorithms, either the Crystal's Dilithium, Falcon, or Sphinx Plus, although NIST does recommend Crystal Dilithium as the primary post-quantum digital signature algorithm. All these algorithms do focus on the difficulty of solving structured lattices, except for Sphinx Plus, which instead focuses on the use of hashing functions. So remember, when it comes to cryptographic attacks, there are 3 main types that you need to consider. These are downgrade attacks, collision attacks, and the threat of quantum computing. A cryptographic downgrade attack is used to force a system into using a weaker or older cryptographic standard or protocol than what it's currently using. A collision attack is going to be used to find 2 different inputs that produce the same hash output by using the principles demonstrated by the birthday paradox. Quantum computing, on the other hand, is more at the theoretical stage today than the practical stage, and it harnesses the principles of quantum mechanics to process vast amounts of information simultaneously in order to enable it to potentially break traditional encryption algorithms like RSA and ECC in just a few seconds by rapidly factoring large prime numbers or solving discrete logarithmic problems. Since this capability threatens the foundational security of our current digital communication and data storage systems, it is one that you should continually read up on and study over the next few years as quantum computing and post-quantum algorithms begin to become a larger part of our enterprise systems and networks.